This is chapter 5, equilibrium of a rigid body, and this is getting into the beginning part's a little bit of review of some stuff that we've already done, the particle equilibrium. So for particle equilibrium, a body is at rest if originally at rest, or has a constant velocity if originally in motion. And this is Newton's first law. We've mentioned this a couple of times this semester. For static equilibrium, that's the body at rest. Case. Later, when we get into dynamics, we'll do some other stuff. But so for this, we have the sum of the forces equals mass times acceleration is the main equation for that, and the acceleration is just 0. So the sum of the forces equals 0. So what that equation there means is that the sum of the resultant of all forces, so if we added up all of the forces acting on a particle, they have to equal 0. In this section, so in section 5.2, they talk about free body diagrams. Free body diagrams are really important for these problems. It is really the first thing that you should do is draw your free body diagram. And the reason that we want to have those is to account for all of the forces known and unknown. So it helps us account for all forces, all the known and unknown ones. And basically the free body diagram is a sketch that shows the particle free from all of its surroundings with all forces acting on it. So we pull out whatever it is that we're interested in, and then we replace anything that was there before with forces or possibly moments. The steps for free body diagrams. Step 1 is to draw the outline shape. Step 2 is to show all forces. Step 3 is to identify each force. And I've noticed y'all not always doing that. Go ahead and give it a name if it doesn't have a name already and identify what it is. Number 4 is to indicate coordinate systems, or the coordinate system. I don't know if you've noticed, sometimes whenever I come around and look at your problem, sometimes I have trouble figuring out where the coordinate, or where you put the coordinate system just because you didn't write it on there. So go ahead and put that on there. You want to include dimensions. And that's it. I guess for this section, I need you to, let's see what page it's on. There's some really important, so to be able to draw these free body diagrams, you need to know, sorry about that, I couldn't find it, page 210 and 211, so page 210 to 211 of your textbook is really important. You need to look through this and understand this, but this basically shows you what different types of connections, the type of reactions that they have. So some of them we'll see a lot and you'll get used to seeing. Some of them are rollers, so they'll be drawn like that or like that. And so if we have whatever thing that we're doing, if you take away the roller, basically you just have a force acting perpendicular to that plane. So for either of those. And that's just one example. A pin's a really common one, a cable. Some of them are on a smooth rod. So the rod restricts where it can go, so it only has a force in one direction, but then it gives a moment on it. A smooth pin is a really common one. Let's see. So it'll often be drawn something like this. And when you have a pin, basically you'll have two forces, or you'll have a force on it that can act in both directions. So it'll either be written like that, or, sorry, it's not exactly the same, or something like this, and you'll have that angle. And then I guess a lot of them are really important, but another one is the fixed support. So for that, you actually have a moment, or you can have a moment and a force that has X and Y component. Or you could rewrite that as the moment. Sorry, I should have a moment. And then you can also have a force that's at an angle. And that's just a different way of saying the force. Alright, so we're just going to do a little bit of practice of this. I'm going to pause it to draw it, and then I want you to draw the free body diagram. Alright, so for this first one, we have the bar AB, and we want to draw a free body diagram of the bar AB. So we're going to first draw that outline. So AB. And then we basically want to remove each of those supports and put in the forces that we'll have there. So at A, we're going to have AX and AY. Then we have that 30-pound force on the top. And then for the roller, we just have it just perpendicular to the surface. And we'll just call that BY. So we replaced all the forces, we just removed that bar, replaced all the forces that we need to. We need to put in the units, right? So the bar is 10 feet long. This force is 3 feet from the end. What else do we need? We need to say what our coordinate system is. So we'll say X, Y. I think that's everything that we have. So I wonder if we could solve these. So something, as you're doing the problems, you first draw the free body diagram, and then you'll think about what equations you have. We have 3 equations for this. So we have the sum of the forces in the X direction equals 0, sum of the forces in the Y direction equals 0, and sum of the moments about a point. So we could do about point A or something equals 0. So we have 3 equations. And if you look up at our free body diagram, we don't know, so our unknowns are AX, AY, and BY. And we know everything else. We know that magnitude and the direction of that 30-pound force. So we have 3 unknowns and 3 equations, so we should be able to solve it. So that one shouldn't be a problem. All right, I'm going to pause it and draw another one. All right, so for this case, we have bar AB, and we have a 50-pound force acting to the left at point B. From point C to point D, we have a cable holding it up, and then they give us some of the dimensions. So let's go ahead and draw the free body diagram for this one. So we're going to isolate AB. So AB, and then let's go ahead and put the forces on it. So we have a 50-pound force here at the ground, so that's a fixed support. So that means that we'll have 3 forces there. We'll have AX, AY, and then a moment about A. So that's just with fixed supports, which we could have seen in that table on page 211. It's example 10. And then we have a cable, which is also on that table on the previous page. And so that cable, we just know there's a force that goes from C down to D. And that force, let's just call it something. We'll also call it the tension in the cable. And we know the CD, let's see, we know it's 16 feet up, 12 feet to the side. So that's actually a 3, 4, 5 triangle. So I'm going to write that on here. Let's see. Other dimensions we know that the height, so from A up to C is 16 feet. And then up to B is 4 feet. So with this one, if we think about sort of what we know and what we don't know, so we basically have 4 unknowns, right? We have TC, we know the direction of it, we don't know the magnitude. We have AX, AY, and MA. So this is considered to be statically indeterminate. And basically what that means is that that there are more unknown loadings on the body than equations of equilibrium for their solution. So we have 4 unknowns. We have 3 equations that we can do with this. Some of the forces in the X equals 0, some of the forces in the Y equals 0, and some of the moments about a point equals 0. So 4 unknowns, 3 equations, so it's considered statically indeterminate. So we've gone through the equations of rigid bodies, equations of equilibrium, just to stress that a little bit more. So equations of equilibrium. Some of the forces equals 0. Some of the moments about a point equals 0. Those are the main equations. If you're in 2D, we have the sum of the forces in the X direction equals 0. Sum of the forces in the Y direction equals 0. And sum of the moments about Z equals 0. If we're in 3 dimensions, we just have more scalar equations we can deal with. So the sum of the forces equals 0. We have sum of the forces in the X equals 0. Sum of the forces in the Y equals 0. Sum of the forces in the Z direction equals 0. We have the sum of the moments about the X-axis equals 0. Sum of the moments about the Y-axis equals 0. And sum of the moments about the Z-axis equals 0. So we can definitely deal with more unknowns in the 3D, but a lot of times in 3D we have more unknowns. And then one more thing to note, the table 5.2 is another important one to show you supports, but this does it in 3D, so supports 3D. So with that, they have like a hinge, a smooth pin, journal bearing, ball and socket's a really common one. Maybe I'll just draw that one. So ball and socket, I'm not going to draw it very well. For the ball and socket, you basically end up with 3 forces. So you have Fz, Fy, and Fx. There's no moment felt there. But make sure you look through all of those and that you have a good feeling for all of those. Those are really important and will help you do your free body diagram. All right, now we're almost finished with just the notes for this chapter. I really recommend that you read through the chapter also. It's really important that all of you have textbooks. Let's see, so 5.4. This section's on 2 and 3. force members. And basically with this, some equilibrium problems can be simplified, or the solution can be simplified if we recognize that some members are subjected to forces only at 2 points. And basically, if we isolate that member, so let's say this is the thing that we got this pipe or something. Let's see. So this is B and A at this end. And we have two forces, FA, FB. But if we isolate that member, AB, we can quickly determine that the resultant forces at A and B must be equal in magnitude and act in opposite directions. And I want you to think about that and why that is. Write this out. So if we take that AB, we know the sum of the forces in the x equals 0 and the sum of the forces in the y equals 0. So if we only have those two forces on there, on that AB, then we know that the forces, in order for the sum of the forces in the x to be equal to 0, the x component of the force at A, let's see, I'll call that AX, has to be equal and opposite in magnitude and direction to BX, and then the same for AY would have to be equal and opposite to BY. And so if we do the resultant of those, then we get, B and A. And it turns out I didn't draw this super well, but these are also along the same line. So you can draw a straight line, and then that gives you that direction. Just ignore my drawing, it's not great. Again, look at the textbook, it has some better ones. And then the last thing I want to talk about are the three force members. So, what am I doing? Three force members. If you do the moment equilibrium for this, what you find, let's see, I'll do a quick drawing. So we've got this beam, and we have three forces. What we know, because of the sum of the moments equal to 0, is if we take the line of each of these forces, so the line along F1, the line along F3, and we know there's a third force on it, then the third force, they're all going to meet at this point 0. So they either have to be concurrent or parallel. So this is an example of being concurrent. So if you take that line of action of each of those forces, then the line of action must pass through that point 0. And at that point 0, the sum of the moments about 0 is going to equal 0. A special case of that is just where they're all parallel. So if we have the same beam, maybe slightly shorter, so I ran out of space. But if we have F1 pointing up, F3 pointing up, and we have F2 pointing down, basically it's the same thing. It's just that the moment, or that point 0, is in infinity. So I think that's it for chapter 5 notes.